This is an online learning (LMS) project. The thought course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Content. In this slideshow, the following topics will be presented: P0 Fourier transform, FT, sinc function, rectangular pulse, exponential function, Fourier transform properties, radar type signal, Gaussian pulse, triangular pulse, real and imaginary parts of a signal, Rayleigh's energy theorem, bandwidth definition, temporal, time, versus spectral. Frequency. Time domain is the analysis of mathematical functions, physical signals, or time series of data with respect to time. For the case of continuous time, the signal or function's value is known for all real numbers. Similarly, in discrete time, its all values are known at various separate instants of time. In electronics, control systems engineering, and statistics, the frequency domain refers to the analysis of mathematical functions or signals with respect to frequency rather than time. A time domain graph shows how a signal changes over time, whereas a frequency domain graph shows how much of the signal lies within each given frequency band over a range of frequencies. The Fourier transform is named after Joseph Fourier. It is a mathematical transformation employed to transform signals between time domain and frequency domain. It is reversible, being able to transform from either domain to the other. Fourier transform of a non-periodic deterministic function, g of t, is given by capital G of f, which is the Fourier transform of g of t, is equal to the integral from -infinity to +infinity of g of t times e to the power -j2 pi ft, integrated with respect to t, where j is the square root of -1. The inverse Fourier transform is defined as g of t, which is the inverse Fourier transform of capital G of f, is equal to the integral from -infinity to +infinity of capital G of f times e to the power j2 pi ft, integrated with respect to f. Fourier transform, angular frequency. Instead of using the frequency variable f, we can use the angular frequency omega, which is 2 times pi f. Using the angular frequency omega, the Fourier transform is as follows: f or omega, frequency units. F is the number of occurrences of a repeating event per unit time. It usually has the unit hertz. Omega is a scalar measure of rotation rate. It refers to the angular displacement per unit time. Omega is equal to 2 times pi f. Notations may vary by source, the book you use. Keep in mind that they represent essentially the same thing. Question: f or omega, frequency units. Find the Fourier transform of the following expression. Give the answer both in hertz and radians per second. G of t is equal to rectangle t. Solution: G of f is equal to sine pi f over pi f. G of omega is equal to sine omega over 2 over omega over 2. Be careful which unit you use. Question: f or omega, frequency units. Find the Fourier transform of the following expression. Give the answer both in hertz and radians per second. G of t is equal to e to the power j omega 0 t. Solution: G of f is equal to direct delta f minus f 0. G of omega is equal to 2 pi direct delta omega minus omega 0. Be careful which unit you use. As you can see, the signals in both time and frequency domain are often complex quantities. This question will test your knowledge about complex numbers. X of t is equal to a times e to the power j w0 t. Find x of t's, real and imaginary parts. Also, find its magnitude. A is a positive real number. Solution. Using Euler's formula, you decompose the complex part of x of t into the real and imaginary parts. To find the magnitude of x of t, you take the square root of sum of the real parts and imaginary parts squares. Finite energy signal, for a non-periodic voltage communication signal across a resistance. The normalized energy is defined as capital E is equal to the integral from minus infinity to plus infinity of square of absolute value of g of t integrated with respect to t. The total area under the curve, square, of absolute value of g of t. Angular frequency omega is equal to 2 pi f. Fourier and inverse Fourier transformed can be shown as linear operators, as seen here. Question. Finite energy signal. Find the energy of the following signal. The following is a rectangular pulse. Its energy is a square times capital T. Question. Finite energy signal. Find the energy of the following signal. The following is a rectangular pulse. Its energy is a square times capital T. Sin function. Consider an integration encountered frequently in calculation of Fourier transform, 1 over capital T times the integral from minus capital T over 2 to plus capital T over 2 e to the power j2 pi ft integrated with respect to t is equal to 1 over j2 pi f capital T times e to the power j2 pi f capital T minus c to the power minus j2 pi f capital T, which is then equal to sinc f capital T. Sinc function is related to the Fourier transform a rectangular pulse, as shown below. This pulse is the most common time signal in digital transmission systems. Maximum of SINC occurs when the argument is 0. Moreover, the zeros of the SINC function are occurring at the points where the argument is an integer multiple of pi. Note that the limit as x approaches 0 of sin x over x is 1. Sin x over x is equivalent to SINC x in the limit condition, which can be seen as scaling the x by pi. Question. Sinc function. Plot the following function. Sin 0.1 x. How to calculate sinc. Sinc is defined as sin pi x over pi x. To calculate the sinc function with regular calculators, first make sure that the input mode is radians, so that when you enter any input value x, it is in radians, not in degrees. Then put down the formula sin pi x over pi x and calculate. Rectangular pulse. We know that capital G of f is equal to Fourier transform of g of t, which is equal to the integral from minus infinity to plus infinity of g of t times e to the power minus j2 pi ft integrated with respect to t. Rectangular pulse, RECT of t, is described as 1 when argument t is between minus and plus 1 over 2 and 0, otherwise. G of t is plotted in this graph. G of t is explicitly equal to capital A times RECT of t over capital T, where capital A is a scalar constant. Fourier transform of g of t is calculated as the integral from minus capital 2 over 2 to plus capital T over 2 of capital A times exponential minus j2 pi ft integrated with respect to t, which is then equal to capital A times capital D times sin of pi f capital T over pi f capital T. So capital G of f is equal to A times t times sinc t. Plotted graph of absolute value of capital G of f can be seen here. Note that the maxima is capital A times capital T and zeros occur at the integer multiples of 1 over capital T. Question: rectangular pulse. Plot the following function. Rect of t over 10. Solution. Note that the function is null before -5 and after +5. Rectangular pulse. Note how we get a continuous spectrum from the Fourier transform of a rectangular pulse function. Also, as one can see from the graph, that short pulses, meaning a small value of capital T, have broad spectra, while long pulses have narrow spectra. Usually take 1 over T as the spectral width, or bandwidth of the signal. Question: rectangular pulse, bandwidth. Find the bandwidth of the signal, rect of T over 10. Solution: rect of T over 10 and 10, sinc 10f, are Fourier pairs. By definition, bandwidth is equal to 1 over pulse duration, which is 0.1. Exponential function. Before writing exponential function, let us define the unit step function. Unit step function. U of t is 1 when t is larger than 0, 1 over 2 when t is equal to 0, and 0 when t is smaller than 0. Now define our exponential function in time domain as g of t is equal to exponential of -a t times u of t. Note that g of t has non-zero values for only non-negative values of the argument t. This is called a decaying exponential. The Fourier transform of g of t is the integral from 0 to infinity of exponential of -at times the exponential of -j2 pi ft. Integrated with respect to t, it is equal to, merging the exponentials, integral from 0 to infinity of exponential of -t times in parentheses a plus j2 pi f. Integrated with respect to t1 integrated with the given limits, it is equal to 1 over a plus j2 pi f. As a result, we get this two-way transformation. Now let us define another exponential function, g of t, this time taking non-zero values only for non-positive values of argument t. This time g of t is exponential of at times u of -t. This is called a rising exponential. The transform is done in a similar fashion, and the result is all the same except the sign of the second term, in the denominator, of the Fourier transform of g of t. As a result, we get this two-way transformation. Question: exponential function. Draw the following functions. Decaying exponential. E to the power -0.1 t times u of t. Rising exponential. E to the power 0.1 t times u of -t. Fourier transform properties. In the following table of properties, unless otherwise stated, whatever the property the Fourier transform has also the inverse Fourier transform. Linearity. The Fourier transform of a times g1 of t plus b times g2 of t is equal to a times capital G1 of f plus b times capital G2 of f, where a and b are constants. Time scaling. Fourier transform of g of at is equal to 1 over absolute value of a times capital G of f over a. Duality. If capital G of f denotes the Fourier transform of g of t, then the function capital G of t has a Fourier transform of g of -f. Time shifting. Time shifting property states that if the function g of t is shifted in the positive direction by an amount t0, the effect is equivalent to multiplying its Fourier transform capital G of f by the factor exponential -j2 pi ft0. The amplitude of capital G of f is unaffected, but the phase is changed by -2 pi ft0. Frequency shifting. This property implies that multiplication of a function g of t by the factor exponential j2 pi fct is equivalent to shifting its Fourier transform capital G of f in the positive direction by the amount of fc. This property is also called the modulation theorem, because a shift of the range of frequencies in a signal is accomplished by modulation. Area under g of t. Area under g of t, that is the area under a function g of t is equal to the value of its Fourier transform capital G of f at f is equal to 0, area under capital G of f, that is, the value of a function g of t at time t is equal to 0, is equal to the area under its Fourier transform capital G of f. Differentiation in the time domain, that is, differentiation of a time function g of t, has the effect of multiplying its Fourier transform capital G of f by the factor j2 pi f. Integration in the time domain, that is, integration of a time function g of t, has the effect of dividing its Fourier transform capital G of f by the factor j2 pi f, assuming that capital G of 0 is 0. Conjugate functions. If capital G of f denotes the Fourier transform of function g of t, then for a complex valued function g of t, we have complex conjugate of g of t is equal to the complex conjugate of capital G of minus f. Note the sign change of the frequency domain function. Here is a useful Fourier transform table, where you can find the Fourier and inverse Fourier transforms of most commonly used functions and expressions. These functions will be used throughout this course. It is very important to learn how to use this table in solving problems. Please bring it to the lessons. Signum function. A time function signum of t is defined as 1 when t is bigger than 0, 0 when t is 0, minus 1 when t is less than 0. That is, signum of t simply identifies the sign of its argument. Signum of t has a Fourier transform of 1 over j pi f. Question. Signum function. Draw the following function, signum t minus 5. Exponential function. Combinations. Exponential function. Combinations. Remember, from previous slides, how we define two different exponential functions. One is the rising exponential for negative x-axis, and the other is decaying exponential for positive x-axis. Now we can combine those two and get a compact form of an exponential function. This is exponential g of t is equal to exponential minus at when t is larger than 0, 1 at t equals 0, and exponential at when t is less than 0. Where is a positive real number? As a one-line expression, the function g of t can be written as exponential of minus a times absolute value of t. Exponential function. Combinations. Remember, from previous slides, how we define two different exponential functions. One is the rising exponential for negative x-axis, and the other is decaying exponential for positive x-axis. Now we can combine those two and get a compact form of an exponential function. This is exponential g of t is equal to exponential minus at when t is larger than 0, 1 at t equals 0, and exponential at when t is less than 0. Where is a positive real number? As a one-line expression, the function g of t can be written as exponential of minus a times absolute value of t. The Fourier transform of this combined exponential function g of t is given as 2a over a square plus square of 2 pi f. Note that, because of the symmetry in the time domain, the spectrum is real and symmetric. This is a general property of such Fourier transform pairs. Exponential function. Combinations. We may define another exponential function as follows. G of t is equal to exponential minus at, for t is bigger than 0, 0 at point t is 0, and minus exponential at, for t is less than 0. A is a positive real number. This function can be written in a compact form as g of t is equal to exponential minus a times absolute value of t times the signum of t. Fourier transform of this function is minus j4 pi f over a square plus square of 2 pi f. In contrast to the Fourier transform pair of previous combined exponential function, this function is odd and purely imaginary. It is a general property of Fourier transform pairs that a real odd symmetric time function has an odd purely imaginary function as its Fourier transform. Question. Exponential function. Combinations. Draw the following function, exponential, minus 0.1, absolute value of t. Question: exponential function, complex. Derive the Fourier transform of the following function, and plot it. G of t is equal to exponential minus 0.1d for positive t, and minus exponential 0.1d for negative t. Solution: note that this function can be written as a summation of two exponentials. Once it is written as a two-term function, you take the Fourier transform of each of them and add them up using linear property of the Fourier transform. Now, let's visualize this function by analytically calculating subpoints of the function g of f and then mark them on the graph. Sin versus rect. Consider the time domain function g of t, defined as capital A times sinc of 2wt. It has a Fourier transform of a over 2w times rectangle of f over 2w. Rect is the rectangular function. Then sinc and rectangular signals form a Fourier transform pair. Question: sinc versus rect. Plot the following function. Then find and plot its Fourier transform. 10 sinc, 10 t. Radio frequency, RF signal, radar applications. Radar type signals are also called radio frequency pulses. They are of the compact form in time domain. G of t is equal to a times rect of t over capital T times cosine of 2 pi fct. Note that in time domain, the cosine function can also be represented as summation of two exponentials, that is, cosine of 2 pi fct is equal to 1 over 2 times, in parenthesis, exponential of j2 pi fct plus exponential of minus j2 pi fct. By applying the frequency shifting property of Fourier transforms, we get the capital G of f, the Fourier transform of g of t, as 8 times capital T over 2 times, in parenthesis, sinc of capital D times f minus fc plus sinc of capital D times f plus fc. For the product, fc capital T is much greater than 1, that is, there is enough separation between two sinc functions in frequency domain. The capital G of f can also be written in a more open form. Capital G of f is equal to a capital D over 2 times sinc of capital D times f minus fc when f is bigger than 0. Capital G of f is 0 when f is 0, and it is equal to a capital D over 2 times sinc of capital D times f plus fc, where f is less than 0. Frequency shifting process is critical for understanding of amplitude modulation. Therefore, it is sometimes called modulation property in Fourier analysis. Question: radio frequency, RF signal. Find the carrier frequency, Fc, of the following RF signal. G of t equal to rectangle t over 10,000 cosine 10,000 pi t. Solution: carrier frequency is written in the argument of cosine. It is equal to 5 kHz. Gaussian pulse. Consider the Gaussian pulse g of t, defined as exponential minus pi t square, defined for all t. In this example, we use the differentiation property of the Fourier transform to derive the particular form of a pulse signal that has the same mathematical form as its own Fourier transform. Let capital G of f denote the Fourier transform of g of t. Then, by taking the derivative of a capital G of f with respect to f in frequency domain, we have the Fourier transform pair minus j 2 pi t times g of t, and derivative of capital G of f with respect to f. If we multiply this above equation by j and Add the Fourier transform pair of derivative of g of t. We get following Fourier transform pair. Derivative of g of t plus 2 pi t times g of t and j times, in parenthesis, derivative of capital F plus 2 pi capital G of f. This equation holds if both sides are equal to 0, because left side is purely real, while right side is purely imaginary. So, we have the following equality. Derivative of g of t equals minus 2 pi t g of t. This then yields the identity g of t equals g of f. Triangular pulse. Triangular pulse. To get a triangular pulse in time domain, first consider the function g1 of t, defined as a times rect of t plus capital D over 2 over capital D minus a times rect of t minus capital D over 2 over capital TC. That the triangular pulse in time domain g2 of t is the integration of g1 of t from minus capital to t plus capital D. To get the Fourier transform of the triangular pulse, we will use the property of integration in time domain. Capital G1 of f is 0, therefore we shall implement the theory as Fourier transform of integral from minus infinity to t of g of tau integrated with respect to tau is 1 over j2 pi f times capital G of f, where capital G of f is the Fourier transform of g of t. First calculate the Fourier transform of g1 of t, that is capital G1 of f is equal to 2ja capital D times sinc of f capital D times sin pi f capital D. Note that g1 of t is real and odd symmetric, therefore its Fourier transform is odd and purely imaginary, whereas the triangular pulse g2 of t is real and symmetric, therefore its Fourier transform is symmetric and purely all. Then using the integration in time domain property we find the Fourier transform of the triangular pulse g2 of t. Capital G2 of f is equal to a times capital T square times square of sinc f capital D. Question. Triangular pulse. Find and plot Fourier transform of the triangular pulse depicted in following figure. Solution. Look at the graph and see that a times t equal to 100. Also, t is equal to 10. So, a is also 10. Using the formula from the previous slides you get the result as 1000 sin square 10f. Real and imaginary parts of a signal, any time domain function g of t, can be expressed as in its real and imaginary parts. So, g of t is equal to real part of g of t plus j times imaginary part of g of t. The complex conjugate of g of t is defined as its real part minus j times its imaginary part. We may employ the conjugate functions property of Fourier transform to easily see the following relations between time domain and frequency domain functions. Real g of t can be written as 1 over 2 times, in parentheses g of t, plus complex conjugate of g of t, therefore its Fourier transform can be written in the form 1 over 2 times, in parentheses, capital G of f plus complex conjugate of capital G of minus f. The same goes for the imaginary part as well. Conjugate functions Fourier transform. G conjugate t and G conjugate minus f are Fourier transforms. Proof. Take the conjugate of both sides in the formal definition of inverse Fourier transform. Then replace the integration variable f with minus f. Note that the limits of the integral changes sign too, because they are defined on the variable f after the variable change. Swap the limits of the integral so you get rid of the minus sign, and the conjugate function's Fourier transform property is proven. Question. Ft of a complex signal x of t equals e to the power j w0 t. Find x conjugate of t. Also, compute x conjugate t's Fourier transform. Rayleigh's energy theorem, ESD. If capital E, energy of signal g of t, is a finite number, then the following integrals are equal to each other. Integral from -infinity to +infinity of square of absolute value of g of t, integrated with respect to t, and integral from -infinity to +infinity of square of absolute value of capital G of f, integrated with respect to f. Energy spectral density of the signal g of t, epsilon subscript g of f, is equal to the square of absolute value of capital G of f. The function epsilon sub of f is a measure of the density of the energy contained in g of t in joules per hertz. ESD, SINC function. Consider again the SINC pulse 8 times SINC of 2 west t. The energy of this pulse, from Parseval's theorem, equals the a square times integral from -infinity to +infinity of square of SINC of 2 west t, integrated with respect to t. The integral on the right-hand side of this equation is hard to evaluate. Therefore we may use the identity we found in the previous slides, that is linking the energy of g of t with its Fourier transform capital G of f. We, therefore, for simplicity evaluate the energy of the signal g of t using its Fourier transform capital G of f, and find that it is equal to a square over 2 west. Bandwidth of a signal. Bandwidth is the difference between the upper and lower frequencies in a continuous set of frequencies. It is typically measured in hertz. A signal is low pass if the spectrum is centered at the origin. A signal is bandpass if the spectrum is centered at the -+fc. Fc is the non-zero carrier frequency communication systems. As an example, a speech signal generated by speaker in radio broadcasting is a low-pass type signal, while its transmitted version via the transmitter is bandpass signal. In other words, in communication systems, bandpass signals are usually modulated versions of low-pass signals. Bandwidth of a low-pass signal, 1/2 of the main lobe. BW of a bandpass signal, null-to-null bandwidth. Example, low-pass versus bandpass signal. If we take the Fourier transform of a low-pass rectangular signal centered at origin, we see that the bandwidth is 1 over capital, where capital T is the duration of the pulse in time domain. But when we modulate, in other words, multiply a rectangular pulse in time domain with a sinusoidal, we see by taking the Fourier transform that the bandwidth is 2 over capital T. Now, where capital is the duration of the pulse in time domain. Question: bandwidth, BW, of a signal. Determine the bandwidth of the following signals. Solution: bandwidth of a signal in bandpass is twice as much compared to low pass. Question: low pass, bandpass. The following low pass triangular pulse is modulated with a carrier frequency of 1 Hz. Sketch the time domain and frequency domain representations of the bandpass signal. Use only the positive frequency axis. 3 decibels bandwidth. 3 decibels bandwidth is a popular definition of bandwidth. It is also called half-power bandwidth. For low-pass signals, 3 decibels bandwidth is defined as the separation between zero frequency, where the amplitude spectrum attains its peak value, and the positive frequency, at which the amplitude spectrum drops to 1 over √2 of its peak value. Here note that the signal is considered to be a voltage or current signal as a communication, but not power signal. This is why we take 1 sqrt2, which is equivalent to 3 decibels of the power of a voltage or current, and so communication signal. In a similar manner, if the signal is bandpass, centered at ±fc, then the 3 decibels bandwidth is defined as the separation between 2 frequencies, at which the amplitude spectrum of the signal drops to 1 over √2 of its peak value at center frequency. The 3 decibels bandwidth has the advantage, similar to null bandwidth, that it can be read directly from a plot of amplitude spectrum. Time bandwidth product. Question: 3 decibels bandwidth. Find the 3 dB bandwidth of the signal, rectangle T, over 10. Solution: You need to find the point where signal is 3 dB lower than its peak time bandwidth product. For any family of pulse signals that differ in time scale, the product of the signal's duration and its bandwidth is always a constant. For a rectangular pulse of duration T in time domain, the Fourier transform shows us that the bandwidth is 1 over T. Therefore the time bandwidth product is a constant. However, note that Bt can change when we use a different definition of bandwidth. For example, if we take first null bandwidth for a rectangular pulse, Bt becomes unity, while when we use 3 decibels bandwidth definition, Bt becomes less than unity.